Right, the next quantum number we want to talk about is the magnetic quantum number, the symbol being m sub L. That should be a lowercase m. It looks kind of like a capital, the way I wrote it there. M sub L. And this quantum number tells you which individual orbital of a given type the electron is in. Because some of with some of the types of orbitals, there can be more than one of them in a given principal energy level. With some, and in fact, the number varies depending on which type of orbital you're talking about. And the possible values for m sub L would be anywhere from negative L up to positive L, including 0. So just to illustrate the relationship between L and m sub L, okay, so if L is, then what are the possible values of m sub L? If L is 0, in other words, we're talking about an S-type orbital, the only possible value for m sub L would be 0. And the fact that there's only one value means that there's only one S-type orbital in each principal energy level. I'm going to say in each shell because I was running out of space. But formally shells are better known as principal energy levels. If L equals 1, in other words, if you're talking about a p-type orbital, the possible values of m sub L would be negative 1, 0, or positive 1. And that's 3 values. And that's because there are actually 3 p-type orbitals in each shell that has them. Not every shell has p-type orbitals. There are no p-type orbitals in the first shell. They start with the second shell. And all of the shells from shell number 2 on out can have p-type orbitals. If L is 3, in other words, if you're talking about a d-type orbital, then the possible, 2, skipped 2. If L is 2, in other words, a d-type orbital, then the possible values for m sub L would be negative 2, negative 1, 0, 1, or 2. And that's 5 values, 1, 2, 3, 4, 5. And that's because there are 5 d-type orbitals. And finally, D3 would be an F-type orbital, and the possible values for that would be negative 3, negative 2, negative 1, 0, 1, 2, or 3. That's 7 values if you count them up. 1, 2, 3, 4, 5, 6, 7. And that's because there are 7 F-type orbitals. And so basically L tells you what type of orbital the electron is in. M sub L tells you which orbital of that type the electron is in. So negative 3 would be a specific one out of the 7 F-type orbitals in any given shell that has F-type orbitals. Or maybe it's in m sub L equals 1. That's a different F-type orbital in that shell, and so on. And so the combination of the 3 quantum numbers that we've seen so far will specify one particular specific orbital in the atom. Okay. Let's see, there is a diagram of the orbitals in n equals 1 through 3 on page 298 in the book. And that would be this diagram here. You can look at, if you have the book, you can look at your own copy of the book to see it in more detail. But so n equals 1 has one orbital in it, and that's an s-type orbital. N equals 2 has two orbitals, well, two types of orbitals in it. It has a single s-type orbital, that's the 2s orbital, and it has three 2p orbitals. And that's what those three numbers there designate. So actually the total number of orbitals in shell number 2 would be 4, a single s orbital and 3 p-type orbitals. In shell number 3, you've got 3 types of orbitals. You've got a single s-type orbital known as the 3s orbital. You've got 3 p-type orbitals known as 3p orbitals. And you've got 5 SPD-type orbitals known as 3d orbitals. Altogether, you've got 5 plus 3 plus 1, or 9 orbitals in shell number 3. And then it goes on like that a little bit longer. You can go into the outer shells, shell number 4, 5, 6, whatever, and you can get analogous situations going on there. So the number of sublevels or orbital types in each shell is equal to the principal quantum number, the shell number. So as we saw, in shell number 1, there's one type of orbital. In shell number 2, there's 2 types of orbitals. In shell number 3, you have 3 types of orbitals, and so far, and so on. So n equals 1 has one sublevel, or in other words, one type of orbital. And that is L equals 0, or S. N equals 2 has 2 types of orbital. L equals 0, which is also known as S, or L equals 1, which is also known as P. And N equals 3 has 3 types of orbitals. L equals 0, which is S, L equals 1, which is P, and L equals 2, which is D. N equals 4 has 4 types of orbitals, L equals 0, 1, 2, and 3. L equals 3 being also known as F-type orbitals. Okay, so the number of individual orbitals of a given type in a given shell is the same as the number of possible values for M sub L. Which also happens to be 2L plus 1. Okay, so as we saw up here, say for 2, if L is 2, the possible values are -2, -1, 0, 1, 2. That's 5 different values. Well, if you take 2L plus 1, That's 2 times 2 plus 1. That's 5. So that's another way to figure it out. The 2L is just because you have the counting up and counting one and basically never mind. 2L plus 1, or just count the possible values of L. If you want to know the total number of orbitals of all types, in a shell, that's just n squared. Because you may have noticed as I was going over the diagram in the textbook a moment ago, for a shell number 1, there's one orbital, one orbital total. Well, 1 squared is 1. For shell number 2, there are 4 orbitals total. There's a single s orbital and 3 p-type orbitals. That's 4 altogether. 2 squared is 4. For shell number 3, there are 9 orbitals altogether. There's the single s orbital, 3 p-type orbitals, and 5 d-type orbitals. Altogether, that's 9. Well, 3 squared is 9. So you can actually tell without actually having to write out the possibilities. Okay, so as an example of some questions that might be asked about this kind of thing, if we're talking about a 5d orbital, that is a d-type orbital in shell number 5, then what would the quantum numbers associated with that be? Well, n would be 5, because that's what this 5 right here means. L would be 2, because that corresponds to a d orbital. And m sub L, since it didn't specify which of the 5d orbitals we're talking about, it could be any of them. So you basically have to list out all of the possible values for m sub L based on L being 2. So m sub L could be -2, -1, 0, 1, or 2. Any of those would be possible. And those are the quantum numbers associated with a 5d orbital. If you specified which 5d orbital you were talking about, then you could pick a single value from this list here, but the question didn't, so we can't. We just have to list them all. Another example might be say, given a list of quantum numbers, which group of quantum numbers is possible, which ones are not possible, and of the ones that are not possible, why? Actually, this specific question sort of clues you in from the very beginning that none of these groups of quantum numbers are allowed. And then the question just becomes why? What's wrong with the list, with each group? So which quantum number in each group is not allowed and why? A is n equals 3, L equals 3, m sub L equals 2. Well, out of this list of quantum numbers, we know n can be any number from any whole number from 1 on up, and so this is okay. The values of L can take values from 0 up to n minus 1. Uh-oh. 3 is n, not n minus 1. So L equals 3 is the impossible value. Now, if L equals 3, it would be possible for m sub L to be 2, because m sub L can be anything from negative L up to positive L. So if L were 3, then M sub L could be anything from -3 up to +3. So 2 falls within that range. So that would be okay. But L cannot be 3. And that's because the maximum value for L is n minus 1. So here, L could not be any greater than 2. If n equals 2, L equals 1, and M sub L equals -2. Okay, n can be any whole number from 1 on up, so this is okay. L can be anything from 0 up to n minus 1. Well, 1 is n minus 1, so that's okay. M sub L, though, oh, that's a problem. M sub L can only take values from -L up to positive L. So the lowest possible value for M sub L, if L is 1, would be -1. Okay, so the lowest value for M sub L here would be -1, not -2. And C, n equals 1, L equals 1, M sub L equals 0. Well, actually, this ends up being very much like the first one. N equals 1 is fine, because n, again, can be any whole number from 1 on up. L, though, cannot be any greater than n minus 1. And in this case, L is n. So if n equals 1, the only possible value for L would be 0. So the maximum value for L, if n equals 1, would be 0. In fact, that's the only value for L. Okay, so there are certain values that work together and certain ones don't. Quantum theory went a long way towards explaining atomic spectroscopy. And the fact that quantum theory was consistent with the known facts about atomic spectroscopy was a big mark in favor of quantum mechanics. Okay. So when an atom in the ground state and the ground state is the way you normally find atoms. All it means is that all electrons are in the lowest energy positions available. And any vacancies would occur in the highest energy positions in the atom, not the lowest. So when an atom in the ground state absorbs the right amount of energy, one of the electrons in a lower energy principal quantum level or shell will be promoted to a higher energy position further away from the nucleus. Okay, so it basically goes farther from the nucleus to a higher energy position. The amount of energy absorbed is the difference in energy between the original location and the new location for the electron. Okay, so that again goes to conservation of energy. The energy that comes from one place goes to another place, and basically it's all accounted for. Nothing disappears, nothing gets created. The atom is now in what's known as an excited state. An excited state is a situation in which there is a vacancy in a lower energy level, and there's an electron in a higher energy level, relative, in a higher energy level where it wouldn't normally be. Okay, so the electron has jumped up to a higher energy position than where you would normally find it. As the name excited state implies, this is an unstable situation. It's a higher energy situation than you would normally have for that element. And what happens is the electron will usually quickly fall to a lower energy position. And that lower energy position could be the location it came from, or it could be a different location, but at lower energy than where it was in the excited state. It won't necessarily go back where it came from, because when you're doing atomic spectroscopy, you often have many of these transitions going on at the same time. So there will often be lots of vacancies in lower energy levels. And so there are lots of places for that electron to fall down to, not necessarily, so it doesn't necessarily have to go back to the same location it came from. And so when the electron falls, the atom releases energy. Often as electromagnetic radiation. Okay, and the energy of that electromagnetic radiation is just the difference in energy between the original position of the electron and the new position of the electron. So the further the electron falls, the greater the energy released. And as it turns out, for any given atom undergoing transitions like this, there are many transitions possible. You usually end up with basically all of them going on at the same time. And that's even for hydrogen with its single electron. That one electron can do a lot of stuff in various atoms. I mean, obviously, for any given atom of hydrogen, there can only be one transition at a time because any given atom of hydrogen only has one electron. But in any given sample of hydrogen, there are going to be a lot of hydrogen atoms. And so at any given moment, you can find hydrogen atoms undergoing all kinds of different transitions simultaneously. And because of that, you will, when you look at the atomic spectrum of hydrogen, you'll see a bunch of different lines. And that's because of different hydrogen atoms undergoing all of these different transitions, basically all at the same time. For hydrogen, we can actually figure out the transitions that lead to changes in energy. And so the change in energy that's released by a hydrogen atom when the electron falls from an excited state to the ground state or to a less excited state would be given by the final energy of the electron minus the initial energy of the electron. So the final energy of the electron would be the lower number, and the initial energy of the electron would be the higher number because it was started out in an excited state and it's ending up in a less excited or even ground state. And to figure this out, we go back to the Rydberg equation. We finally explained what those numbers mean in the Rydberg equation. The first number on the bottom, Rydberg knew that it was a whole number squared, but he didn't know what it meant. What it actually means is the principal quantum number of the final position of the electron. And what the denominator, the whole number that was the denominator for the other part, the other fraction, that's just the principal quantum number of the original position of the electron before it fell. So say if an electron falls from n equals 6 to n equals 2, well, n initial will be 6, and you'll have to square it. And then n final would be 2, and you'll have to square that also. And then you multiply that by this, and you've got the change in energy. So it's the energy of the photons being released that determine their wavelength and frequency. Okay, so if you have the energy of the electromagnetic radiation being released, you can determine the wavelength and frequency. And we'll see an example of actually doing that in just a moment in the next segment of the video.